Welcome to our CVPR 2026 presentation. We introduce a differential adaptive 4D structured illumination framework for the joint capture of shape and reflectance. Structured light is a gold standard for 3D capture. Usually, spatial structured lighting uses projectors to capture geometry. Meanwhile, angular structured lighting uses LED arrays to probe surface materials. Can we combine them into a single device? Recent work proposed a prototype with an LED array and an LCD mask to do exactly this. However, it still captures geometry and appearance in separate passes. Furthermore, the scanning is highly inefficient due to single LED exposures, and it relies on pre-optimized patterns that cannot adapt to the object. To overcome these limitations, we introduce a truly 4D structured illumination framework. We encode both spatial and angular information into the very same photograph. Take a look at our capture process. No scanner has ever used patterns quite like this. By multiplexing multiple LEDs at once, we dramatically reduce acquisition time. More importantly, the patterns are generated on the fly, adapting perfectly to the specific object being scanned. How does it work? Our pipeline is split into two stages. First, in the differential adaptive acquisition stage, we maintain a pixel-wise probability model tracking the uncertainty of both depth and reflectance parameters. Using this model, our system automatically computes the optimal next light and mask patterns. It does this by minimizing a cross-entropy loss that encourages the maximum reduction in depth uncertainty. We then physically project this optimized pattern, take a photograph, and use the new physical measurements to update our probability models. As this closed-loop process repeats, projecting, measuring, and updating, you can see our probability histograms continuously refine, rapidly converging toward the ground truth. Once acquisition is complete, these concentrated probability models provide an excellent initialization for our second stage, joint fine-tuning. This stage minimizes the difference between physical and simulated measurements to output the final, high-fidelity depth and texture maps. We evaluated our framework on a variety of physical objects. For geometry, our depth reconstruction compares favorably against state-of-the-art techniques. At the same time, our recovered reflectance parameters render photorealistic results that closely match actual photographs. Notice the zoomed-in details here. Compared to previous methods, our adaptive multi-LED approach reconstructs much cleaner surfaces, significantly reducing banding and shadow artifacts. For more details and results, please check out our paper. Thank you for watching and see you in Denver.